In this video, we're going to take a look at one more method of how to do our apportionment rounding, and then we're also going to take a look at what we see on the board, which is representative share. So first, we're actually going to skip this for a second. We'll come back to it. So the last method of apportionment method is called the Hill-Huntington method. Before we get into the Hill-Huntington method, we have to review something that you heard in your geometry classes, but likely have forgotten since then. So what we need to do is find what we call the geometric mean. The way to get the geometric mean for two numbers is a two-step process. Step one, take your two numbers and multiply them together. Step two, square root what you get. So for this method of rounding, the Hill-Huntington method, the first thing we need to do is when we find our quotas, if I give you a quota of 31.72, we need to get the geometric mean of the lower quota and the upper quota. So the lower quota is when we round down, that's 31.72. The upper quota, that's when we round up, is, sorry, the lower quota is 31. The upper quota is 32. So the geometric mean, which we'll represent by Q star, is when we take 31, multiply it by 32, and then we take that number and square root it, which comes out to 30.496. So this is a skill that we need before we can even make it into the next part of our conversation here. So with the Hill-Huntington method of apportionment, first we get our standard divisor, we get the quota, and we get the geometric mean of the lower and upper quota. Let's start with that much, then we'll come back to step two. School district has three high schools with CR3 states. They wish to apportion 100 math teachers based off a school's enrollment using the Hill-Huntington method of apportionment. So first we get our standard divisor, as always, population divided by apportionment. So our standard divisor is 85.9. We get our quotas, which is our population divided by the standard divisor, 28.17, 39.69, and 32.10. So the next one where it says the rounding point, that's when we take the geometric mean. We're not going to need this area. We're not going to need this area for this question, and we'll see why in a second, but I could do the work here. So the first one, we're going to take the square root of 28 times 29. That comes out to 28.49. The next one, we take the square root of 39 and 40, because that's the lower quota of 39.69 and the upper quota. So that comes out to 39.49. And the last one would be the geometric mean of 32 and 33. So we multiply 32 times 33 and we square root it, we get 31.49. You'll notice a pattern. Most of the time it ends in 49. Not every time, so we still have to actually punch in the calculator, but most of the time it does. And so here's how we round. We're not going to do a true round of 0.5 goes up, 0.49 goes down. We're going to look at the quota, and we're going to look at the rounding point. If the quota is bigger, and this, if you're following along in your notes, this is step two. If your quota is bigger, we round up. If the rounding point is bigger, we round down. So in this case, 28.49 is bigger than 28.17, which means those 28s round down. 39.69 is bigger than 39.49. So in this case, those 39s round up to 40. And this last one, 31.49 is bigger. So since that side is bigger, oh, sorry, that should have said 32.49. Since 32.49 is bigger, we round up to 32, and that's our 100. we're good to go. If that was step 3, adding the rounded quotas. With any luck, when we add up those rounded quotas, it will equal our house size, that 100. This next one, we're not so lucky. This right here is actually an example of a really hard question. I'm actually going to give you a little more information here than I normally would. So first, obviously, we find our standard divisor. That's 17,600 divided by 200. And we get a standard divisor of 88. We get our quotas. 5,000 divided by 88 is 56.81. 3,550 divided by 88 is 40.34. Then we get 49.4 and 53.40. Then we get our geometric means. So for this first one, we'll take the geometric mean of 56 and 57 because that's our lower and upper quota. Multiply them and square root, we get 56.49, 40.49, 49.997. We'll see in a minute why I went to 3 decimals for that one. 53.49. So now we do our rounding. Sorry, that's 0.40. So this first one, that's bigger, so it rounds up to 57. That's bigger, so it rounds down to 40. That's bigger, so it rounds up to 50. I'm sorry, that rounds down to 49. And then that one also rounds down to 53. That adds up to 199. What's the problem? We need it to add up to 200. So just like the Jefferson method, if this number needs to go up, this 199 needs to go up, we're going to modify our divisor. Instead of using the standard divisor, we will use a different divisor. And again, because that number needs to go up, our divisor goes down. If this number had, say, been 201, then we would bring our divisor down. So because this number needs to go up, we bring our divisor down. And on a tester quiz, you have to try a bunch of different numbers. I will tell you this one is a very specific problem. In order for this to work, we need to make our divisor 87.88. I'll write that a little clearer. So I'll do my Q here, my Q star here. Sorry, there's no good way for me to write this. Q, Q star, D is 87.88. And then I'll put the rounded quota here. Sorry about that black line, that darkened one. That we do not need to worry about that darkened black line right there. We're just going to ignore it. So now our quotas, if I use 87.88, are 56.89, 40.38, 49.499. This is why I did the geometric mean to 997 over there. And 53.48. Our geometric means, lucky for us, didn't change because this 56 is still geometric mean of 56, 57. Sometimes they change and sometimes we do need to calculate new geometric means. So the geometric mean is still 56.49, still 40.49, still 49.997, and still 53.49. Had say this number jumped up to 54.2 or something like that, then we would need the geometric mean of 54 and 55. Lucky for us, none of our Qs changed quotas, changed lower or upper quotas. If the lower or upper quota changed, we would have to redo our geometric means. I'll just redraw the columns in here. And so then we compare. We get that side's bigger, so we round up to 57. We get that this side's bigger, so we stay rounded down to 40. You see why I went to 3 decimals here, because this side is ever so slightly bigger, which gets us to 50. And then this side is bigger, which means we are staying down at 53. Now it adds up to the 200 that we want. So these questions can be time consuming. Every time this doesn't add up, we have to pick a new divisor and start the process over. We got to get new geometric means and new quotas and new rounding. So let's do one more. I get my standard divisor, which is in this case 140 divided by 20, which is 7. So when I divide all these guys by 7, I get 3.57, 4.57, 5.42, 6.42. Then I get my geometric mean. The geometric mean of 3 and 4 is 3.46. Geometric mean of 4 and 5 is 4.47. Geometric mean of 5 and 6 is 5.47. And then 6.48. Then we do our comparisons. That's bigger, that's bigger, that's bigger, that's bigger. So the first 2 round up. Second 2 stay rounded down. That adds up to 20. Thank goodness we do not have to go any further. Again, if that didn't add to 20, we'd have to alter our divisor and determine if we needed to go higher or lower, get new quotas, get new geometric means, and start all over. So that is it for the Huntington method of rounding. That's our 4th and final method. We have one more thing that can be added on to the end of any method, which will be our final video of the chapter.